Okay. Here's the way I label this. I label this a little bit different than the book, but it won't hurt to read what I'm doing and what the book's doing. So I have these two loops, the two segments, A1 and A1 prime, and the segment A2. Okay? And I claim that A1, that area, is the A2, that area. There are two segments. And all segments are simple, right? A1 is the A2 as the square of their corresponding parts. Well, A1, if you complete this triangle here, I'm trying to not clutter my drawing. If you complete that triangle there, the base of A1 has a characteristic dimension r small, right? This is the picture that I'm looking at. This is r small, so this is also r small. (90°). Okay, let's go find another one. This is 90°. We said that was a square. A lot of this is left out of the book. This is 90°, right? So now I have another one of these things, 90°. That's this 90°. And this is r big. And this is r big, right? R big up this way, R big up this way. And then I have that segment. I claim, because this angle is the same, the areas of these segments are in the ratio r small squared to r big squared. Does that seem plausible? If you assume that area figures are proportional to squares of characteristic lengths, in this case the radii here that define these segments, that's true. What is r big in terms of r small? This is r small, this is r small, that's r big. I claim r big is the square root of 2 times r small, right? Pythagorean theorem, r small squared plus r small squared is 2r small squared equals r big squared. So hence r big is the square root of 2 times r squared. So the ratio A1 to A2 then is r small squared to square root of 2 times r small, that quantity squared. It's 1/2, right? A1, in other words, is 1/2 A2. So we have that. All right. You geometry teachers are really happy with this? It's okay? All right. So A2. Right. I can't begin to tell you where we're at, but I'll give you my notes. A2, since A1 is half of A2, this plus this must be A2, right? So this area and this area actually now equal that area. So the two little segments equal the big segment. Okay. All right. The area of the loop. Remember the loop? I'm just going to very coarsely shade it, so concentrating on the area of the loop is equal to A1 plus A1 prime plus let's call this piece A3. That's this kind of portico, gable end looking arch thing, okay? Plus A3. Okay. However, we just said that A1 plus A1 prime is A2, right? What is A2 plus A3 on the drawing? It's this to here. All the way. That looks like exactly what you say, half the area of the big square here, right? Okay. What's the area of the big square? R big squared, right? So area, what do we call it? It's the square is R sub big squared. And R sub big squared is 2R sub small squared, right? And we just said that A2 plus A3 is half of that. So A2 plus A3 must be half of twice R sub small squared. So it just must be one of them. So Hippocrates' theorem basically is contained in this statement. The area of the loom is equal to the, this is small, is equal to the area of the defining circle squared. No, sorry, it's the defining circle squared. So the loom has the same area as that square. Okay? Now, who would like to look at, there's another one that we can do. It's on page 4. 4C. This one. Somebody want to tackle that one for Thursday? Who wants to bid on that? Come on. Brock, you're good. Okay. Okay. You want to show why? What are they actually saying here? It looks like Mickey Mouse, but what is the implied theorem? That these two little looms have the area of that triangle, right? Okay, so we'll hear from you on Thursday or so about that. All right, good. 7C is going to do it. You can also do it, and then you can convince, show them how he's going to go. Okay, that's interesting. You'll notice there was an assumption in there. There was an assumption in there about the area of similar figures is in the ratio of the square of the linear, linear dimensions. Eudoxus actually attacks that. He tries to, and successfully, with the aid of a very, very self-evident axiom, shows that that has to be true when you extend it to figures that have curves. Anybody can do it for a triangle, right? If I have a triangle with sides A, B, and C, this doesn't have to be a right triangle, but so what, maybe it is. And then I have another one with A prime, B prime, and C prime. And they're similar, which means these angles are the same, right angle, same, right, respectively. The ratio of the two areas goes as what? The ratio of the big one to the small one is what? A prime squared over A squared, B prime squared over B squared, C prime squared, C squared. What if we had this altitude drawn to the hypotenuse and call that H? This would be H, this would be H prime. Sure. Unfortunately, these guys didn't have true. So, anyway.